Okay, a little bit different video today. I want to talk about the limitations of the different variable types in Java and in most computer languages. And in order to do that, we need to understand, or we need to be reminded about how binary works. I talked to you guys about this last semester just a little bit, but I think this time we really should understand it. Because Python didn't bother us about the sizes of our numbers. You can put as big a number as you want in Python, and Python figures it out. Older languages like Java and C are not like that. So the first thing we need to remember is how our number system works. If I write a number like 2,547, okay, what does that mean? It is a sum of numbers with different decimal values. It is 2 times 1,000 plus 5 times 100 plus 4 times 10 plus 7 times 1. And we need to do that because the system of numbers that we use is a decimal system and it only has 10 digits. So when you get up to 10, you have to start over. And the reason our number system has 10 digits is because we have 10 fingers and we started by counting things on our fingers. There's no other reason that we start over at 10 than we used to count things 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you're out of fingers and you have to start over again, 11, 12, 13, 14, 15. We take that for granted because we learned numbers so long ago when we were, 4 years old, that we don't really think about the fact that there's other ways you could do it. You could start over wherever you want. You could have a base 8 system. You could have a base 12 system. Computers use a base 2 system. Computers only have 2 fingers, as it were. They're made of circuits that can be either open or closed. They can either have current running through them or no current running through them. So their numbers that they understand are 0 and 1, on and off, are the only numbers that a computer understands. So whereas we express things in terms of powers of 10, right? 2 times 1,000 is 2 times 10 to the 3, right? 1,000 is 10 cubed, and 500 is 10 squared, and 10 is 10 to the 1, and 1 is 10 to the 0. So we express our numbers as multiples of powers of 10, 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3. Computers only have 2 digits, and they express their numbers in terms of powers of 2. So if I write a number like 10101 in binary, what does that mean? That means a certain number of 2 to the zeros, and a certain number of 2 to the ones, and a certain number of 2 to the twos, and a certain number of 2 to the threes, and a certain number of 2 to the fours. Okay? It's the same idea, just we have way fewer digits. So what is this? This is, we'll start at this end this time. This is 2 ones, no twos, 1, oh no, that's wrong. Let's try again. That is 1, 2, it's the same number, but I wrote it down wrong. That's 1 times 2 to the 0, that's 1. 0 times 2 to the 1, that's 0. 1 times 2 to the 2, that's 1 times 4, that's 4. 0 times 2 to the 3, that's 0. And 1 times 2 to the 4. What's 2 to the 4? 2, 4, 8, 16. So this number, 10101 in binary, is 1 plus 4 plus 16, which is 21. Are we sure about that? Let's go to the computer and check really sure, make sure we didn't make any mistake. 21 in binary is 10101. Okay. So the way you express a number in binary is with ones and zeros, and each of those digits represents a power of 2. 1, 2, 4, 8, 16, 32, 64, 128, 256. I've said last semester that it's not a bad idea to memorize your powers of 2, at least up to like 2048 or so, if you're going to be doing lots of computer science. It's useful to do. Excuse me, let me grab my drink. How big of a number can we express with a certain number of digits? with, say, in base 10, the numbers that we're used to using. How many numbers can we express with 2 digits? We can express from 0 to 99. How many can we express with 3 digits? We can express from 0 to 999. This is 1 less than 100, right? This is 10 to the 2 minus 1. This is 1 less than 1,000. That's 10 to the 3 minus 1. So with n digits, we can express up to 10 to the n minus 1 with n decimal digits. It's the same with binary. With binary digits, we can express up to 2 to the n minus 1. Let's see what that looks like. What can we do with 2 binary digits? With 2 binary digits, we can express the numbers up from 0, 0 to 1, 1. What's 1, 1? It's a 1 and a 2. That's 3. What can we express with 3 binary digits? We can express from 0, 0, 0 up to 1, 1, 1. Right? What's 1, 1, 1? It's a 1 and a 2 and a 4. That's 7. What can we do with 4 binary digits? We can express the numbers from 0, 0, 0, 0 up to 1, 1, 1, 1. What's the number 1, 1, 1, 1 in binary? It's a 1 and a 2 and a 4 and an 8. That is 12, 13, 14, 15. Well, this is 2 squared minus 1. And this is 2 cubed, which is 8, minus 1. And this is 2 to the 4th, which is 16, minus 1. So we can express a number up to 2n minus 1 with n binary digits. And another name for a binary digit is a bit. So a bit in computer language is just a 1 or a 0, an on or an off, okay? A binary digit. So this brings us to storing information in a computer. When you store information in a computer, you store it with a certain number of bits. I think we talked about the fact that the old Nintendo, the original Nintendo, the NES, you sometimes hear those referred to as 8-bit games. What does that mean? That means every pixel on the screen is stored with 8 bits of information that define the color. When you store data in a variable, it used 8 bits to store the data. How big of a number can you store in 8 bits? It's 2 to the 8 minus 1. What's 2 to the 8th? It's 2, 4, 8, 16, 32, 64, 128, 256. So 2 to the 8 minus 1 is 255. Okay? That's the biggest number you can store in 8 bits, which is also called a byte. You can store a number from 0 to 255. And the example I gave last semester is, if you know your classic video games, you may know that in the original Legend of Zelda game, your coins, your money was called rupees. And how many rupees could Link have in his inventory? The maximum number of rupees that Link could have in his inventory was 255. Why? Because the original Legend of Zelda game used 1 byte of data to store the number of rupees that Link had in his inventory, and that number maxes out at 255. If you were a 13-year-old in 1986 or whenever and didn't know anything about binary or bits or how computers store information, that might have seemed a weird number. Why not round it off to 300? Because 300 would require 9 bits of data to store that. So there's a reason for that number. There is also a reason that in languages like Java and C, your numbers are limited to certain sizes, because the different variable types use a certain number of bits to store their data. And I don't have these memorized, so I'm going to occasionally consult my notes over here. Excuse me. An int in Java stores data with 32 bits of information. And you might say, well, that means you can store numbers from 0 to 10 to the 32 minus 1, right? Not quite. Because one of those bits is reserved for the sign. And the other 31 bits are reserved for the number. Okay, so you have to know if the integer is positive or negative. That takes one bit, right? One piece of information, plus or minus. And then you've got 31 bits for the number. So this should be 2 to the 31 minus 1. I'm just going to go to my calculator here really quickly and type in 2 to the 31th power. It's 2147. Hope I don't run out of room here. 2147 483,648. 8364, and then if I take away 1, I get 7. So that's about 2.1 billion. And now I'm going to check my notes and make sure that that number is right. 2147 483,647. Okay? So when using ints in Java, that's the biggest number you can use. Which is why when we did Project Euler, the Project Euler problem where you add up the first 2 million primes or whatever, we couldn't just use an int because an int runs out of room a little more than 2 billion. What happens if you go over 2 billion? If you put an int in your Java program and then keep adding stuff up beyond 2 billion, what happens is it actually wraps around to the bottom and you'll start getting negative numbers like negative 2 billion and negative 1 million and negative, and you'll think, why this number should never be negative? Why am I getting negative numbers? It's because you've gone past the ceiling of the number of bits you're allowed to use for a number, and you've come back around the other side again. So if you start getting negative numbers when you're doing math with big numbers, when you're writing a program, that's probably why. That's called an overflow. You have overflowed the capacity of an int, and then it wraps around and starts giving you negative numbers instead, and that's usually not what you want. So an int uses 32 bits in Java, which most of the time, most programs you write, you're not going over 2 billion in your numbers. The whole point of Project Euler problems is they force you to use bigger numbers than computers are comfortable with. If you need longer than that, then you use a kind of variable called a long integer, or just a long in Java, which uses 64 bits. And just like the int reserves 1 bit for the sign, this gives you numbers from plus or minus 2 to the 63 minus 1. 2 to the 63 is a huge freaking number. What is 2 to the 63? 2 to the 63 is 9.22 times 10 to the 18th. That's 9 trillion. Okay, or 9, was that quintillion? We don't use names. Scientists don't use names once you get above a trillion. That's 9 times 10 to the 18th. It's 9 quintillion, from plus 9 quintillion to minus 9 quintillion. In the real world, you will seldom need numbers that are on the order of 10 to the 18th. If you're an astronomer, maybe you'll need numbers that are bigger than 10 to the 18th. You're talking about the number of stars in the entire universe. That's not even quite that. That's 100 billion times 100 billion. That's only 10 to the well, is that? Yeah, you might need it if you're an astronomer. You might need a number that big. Okay, so this is why in Java we have to be careful when we're declaring our variables, that we declare them of the right type and we know how big they're going to be. It also goes the other way. If you really want to save storage space in data in a Java program, there are actually kinds of numbers that use fewer bits than an int. If I ask you to guess what the kind of variable that uses fewer bits instead of a long integer, And I asked you to guess, you might guess right. That is called a short integer. You can declare a variable in Java of the type short. A short only uses 16 bits. So that can only store from plus or minus 2 to the 15th, right? 1 bit goes to the sign, minus 1. 2 to the 15th, this is 32,767. So 32,000. If you're doing a program and you only know that your numbers need to go up to 32,000, make your variable a short instead of an int. It saves the program storage space. Why would you want to do that? Why would it matter? Like, does it matter whether we use 16 or 32 bits to write our Java program? Not if we're just running code to run in a little window in our Code.hs browser. But remember, the whole point of Java is that it's portable. You should be able to run it on any system. If you're running an app to run on a watch, it might matter whether your data uses 16 bits or 32 bits. You want to make that data as small as possible to take up as little memory as possible. So you can even go smaller than that. You can actually define a variable in Java to be a byte. A byte is just 8 bits. Which means, remember the 255 from Legend of Zelda, because 1 bit goes to the sign, it can only go half as much as it goes up to plus or minus 127. Okay? So if you know you're going to have a number that's never going to be bigger than 127, you could declare it as a byte, and you won't get an overflow as long as you don't accidentally make that number 129. So this is important to know when you're writing programs, that you want to keep an eye on the size of your variables and make sure they don't exceed these limits. We didn't have to do this in Python again. We just created a number, it knew it was an integer. If you want to make it 100 trillion, just do that. And behind the scenes somewhere, Python just allocates more memory to that variable as needed. Java doesn't do that. By the way, it's worth mentioning just in passing, if you ever take a course or ever find yourself going from, say, Java to a language like C or C++. Java and C++ also have variables like unsigned int. An unsigned int doesn't reserve that extra bit for the sign. So where an int in Java can go from, my lights just went out here because I've been sitting still too long. An int in Java can go from 32,000 to 32,000-ish. An unsigned int can go from 64,000 to minus 64,000. Twice as many, another power of 2, because it doesn't use a bit for that sign. Java doesn't do that. I don't know why Java doesn't do that. Java doesn't have unsigned ints and unsigned longs. C and C++ do. That's just something it's just a word, unsigned integer, to hold in your head in case you ever learn some other language other than Java. Java doesn't let you do that. Everything I said about ints and longs and shorts also goes for decimal numbers. We haven't talked about decimal math in this class in 222 yet, but we will talk a little bit about it probably next week, maybe the week after, and talk about floating point math and floating point errors and stuff. You can have a float in Java. I don't know off the top of my head what the range of floats is in Java. A float can save numbers ranging from 1.4 times 10 to the minus 45th up to 3.4 times 10 to the 38th. Okay, is the range of variables. But the other question is, how many decimal points does a floating point decimal have in Java? And the answer to that is that a float in Java has, and again, these are not numbers I have memorized, they're not numbers I expect you to have memorize, only has about 6 digits of precision. So 1.234. That's not very many. Why does it say 6 or 7 digits? Because it depends on if you're in decimal or binary fractions. That's the float. There is a better, more precise kind of decimal number in Java called a double precision floating point number, which has more like 15, 3, 4, 5, 6, 7, 8, 9, 8, 7, 6, 5. Okay, it has 15 or 16 digits of precision. I will probably, because that's not very much precision, I will probably almost always declare my decimal numbers in Java to be doubles. There's no reason not to. Again, we're not trying to save memory. It doesn't matter if we're using 16 or 32 bits for our floats. So I will probably only rarely declare something to be a float. I'll probably almost always declare it to be a double. I don't know if Java has anything more precise than a double. I know, I think C and C++ have a double-double, which has got 31 digits of precision. It's all a question of how many bits you're allocating to storing that number, how many bits of memory it takes up, okay? So that's all I'm going to say about that. You should be able to, I don't know how because this is an online class, I don't know how I'm going to test you guys on this. You could just look it up in your calculator, but you should be able to, if I give you a number like 1101011, you should be able to convert that into binary, from binary into decimal without a calculator. I'm not saying you should be able to do it fast, but you should be able to do it. So what is that number? It's 1 plus 2 plus no 4s plus an 8 plus no 16s plus a 32 plus a 64, right? And that's what? That's 10, 8 and 2 is 10, 42, 106, 107. See if I can do that in my head well enough. Pull up my computer. What is 107 in binary? 1101011. Yeah, I got it right. Okay, so you should be able to do that. Again, I don't feel like I can probably ask you a question on a quiz or exam because this is an online class. You can just go look it up somewhere. Your calculator can probably do it too if you dig into how your calculator works. But if you're going to go on and continue to study computer science, it's something you should know how to do. Okay, so I'm going to go ahead and stop that there, and then we'll get back to programming shortly.